Welcome to Elementary Real Analysis. Today we are going to explore one of the most profound and foundational ideas in all of mathematics, the completeness property. If you have ever wondered what truly separates the real numbers from the fractions you have used for years, this is the answer. We will build this concept from the ground up, so do not worry if it sounds intimidating right now. By the end of this lesson, you will understand exactly why the real number line is perfectly solid and why this single property makes all of calculus possible. Let us dive in. Before we look at any math, let us build a mental picture. Imagine walking across a river on stepping stones. You can step safely, but there are gaps between the stones. The rational numbers or fractions are exactly like those stepping stones. There are infinitely many of them packed closely together, but they still have microscopic gaps. Now, imagine a perfectly smooth, solid concrete path across that same river. That is the real number line. There are absolutely no holes, no gaps, and no missing pieces anywhere. The completeness property is the mathematical guarantee that the real number line is completely solid. Now that we understand the visual difference, let us define a few simple terms to describe this mathematically. First, imagine a collection of numbers, which we call a set. If this set has a ceiling, meaning no number in the collection goes higher than a certain value, we say the set is bounded above. Any number that acts as the ceiling is called an upper bound. But there can be many ceilings. The smallest possible ceiling, the tightest boundary that still keeps all the numbers underneath it, is called the supremum, or the least upper bound. This brings us to the formal mathematical statement of the completeness property. Conceptually, this formula simply says that if a group of real numbers has a ceiling, there is always a perfectly exact lowest possible ceiling that belongs to the real number family. Let us break down the symbols. S is a non-empty collection of real numbers. The symbol M represents an upper bound, which is our ceiling. The inequality tells us that every single number inside our set is less than or equal to this ceiling. If these conditions are met, the property guarantees that the supremum, the absolute tightest boundary, exists and is a valid real number. If the set grows, the supremum might shift, but it will never fall into a gap. Let us look at a visual representation of the formula we just discussed. Here, you are seeing a number line. The shaded region on the left represents our set S. Notice the points scattered to the right of the shaded region. These are all valid upper bounds, acting as ceilings for our set. But look at the exact point where the shaded region ends. That specific dot is the supremum, the least upper bound. The completeness property guarantees that this specific dot is a real number that actually exists on the line, ensuring the boundary is perfectly solid. Before we move on to complex ideas, let us see this with a concrete example. We will find the supremum of a very basic collection of numbers, the set containing 1, 2, 3, and 4. We want to verify exactly how the completeness property applies here. First, we check if the set is empty. We can clearly see it contains 4 distinct numbers, so it is not empty. Next, we must look for upper bounds, which act as ceilings. We need numbers that are greater than or equal to every single number in our set. Continuing with our simple set, we need to identify those ceilings. Any number that is 4 or larger is considered an upper bound. For example, 4, 5, 10, and 100 all work perfectly as ceilings because no number in our set is larger than 4. Since we can find at least one upper bound, the set is officially bounded above. Out of all the possible ceilings we just listed, the number 4 is the absolute smallest one. Therefore, 4 is the least upper bound, or the supremum. Because 4 is a standard real number, this perfectly demonstrates the completeness property in action. Now that we have built confidence with a simple case, let us consider a much more important example that shows why fractions alone are not enough. We are going to look at a specific collection of rational numbers. This specific problem is famous because it reveals the hidden gaps in the rational number system. We will see that if we only use fractions, certain sets will have boundaries that simply do not exist in our number system. This failure will prove exactly why the real numbers need the completeness property to fill in those microscopic holes. Let us define this famous set mathematically. We will call our set A. Conceptually, this formula gathers all the fractions whose square is strictly less than 2. Let us look at the symbols. The symbol Q represents the rational numbers, which are any numbers that can be written as a simple fraction. The condition x squared is less than 2 is the rule for entry into our set. For instance, the number 1.4 is included because its square is 1.96. However, 1.5 is not in the set because its square is 2.25. Let us test if this set has a ceiling. We already know that the square of 1.5 is 2.25, which is strictly greater than 2. Therefore, no number inside our set A can possibly be larger than 1.5. This means 1.5 acts as a valid upper bound, proving that the set is bounded above. According to the completeness property, because the set is bounded above, a supremum must absolutely exist. But what exactly is that tightest boundary? So we have proven that an upper bound exists. This brings us to finding the exact supremum. We are setting out to find the absolute tightest boundary for numbers whose square is less than 2. Mathematically, the exact boundary must occur exactly where the square of the number equals to. Solving this simple equation tells us that the boundary is the square root of 2. This step is crucial because it pinpoints the exact mathematical value of our ceiling. We have found the supremum, but this creates a massive problem if we restrict ourselves to the rational numbers. Let us see why in the next step. Continuing our derivation, we must look at the nature of our boundary. The square root of 2 is an irrational number, meaning it cannot ever be written as a fraction. If we only lived in the world of rational numbers, this set would have no supremum because the exact boundary falls into a missing gap. The rational number line simply does not have a point for the square root of 2. The completeness property of the real numbers fills this gap. It ensures that the square root of 2 exists to act as the perfect, solid boundary. This proves why the real numbers are fundamentally different and complete. Now that we have seen how the property fills the gaps, let us understand why this matters in the real world. The completeness property is the absolute bedrock of advanced mathematics and calculus. Without it, the concept of a limit would completely fall apart because a sequence of numbers might try to converge to a target that simply does not exist. In physics and engineering, when we model continuous motion, like a car driving down a highway or a planet orbiting a star, we rely on the real number line having no gaps. If the number line had holes, an object moving from point A to point B would mysteriously disappear at the gaps. We have covered a lot of ground today, so let us review the key takeaways. First, the completeness property is what makes the real number line a solid, unbroken continuum. It guarantees that any non-empty set with a ceiling has a precise, lowest possible ceiling called the supremum. Second, this property separates the real numbers from the rational numbers by filling in all the microscopic gaps. Because of this, we can confidently perform calculus, calculate limits, and model the continuous physical world without fear of missing numbers. You have now mastered the foundation of real analysis. Great job!